In this video, we focus on solving homogeneous, linear systems of differential equations. For us, this will mean a pair of differential equations that can be written as follows. Here, a, b, c, and d are all constants. We can write this homogeneous linear system of equations in matrix vector form as u prime of t set equal to a times u of t, where a is a 2 by 2 matrix of constants. Recognizing that the problem here involves a matrix is important because, as you will see over the next few lessons, how we solve systems of differential equations like these depends on the eigenvalues of A. For now, let's restrict our attention to the case in which A has two distinct real eigenvalues, say lambda 1 and lambda 2. Because they're distinct, lambda 1 is not equal to lambda 2. If v1 is an eigenvector associated with lambda 1 and v2 is an eigenvector associated with lambda 2, then the solution to u prime is equal to a times u takes the following general form. Here, c1 and c2 are constants whose value is determined by an initial condition associated with the given system of differential equations. Let's now look at an example to see how this formula can be applied. Consider the following system of differential equations. With this condition placed on the value taken by the unknown functions when t is equal to 0. If we were to write out the given differential equations in matrix vector form, the equation would feature the 2 by 2 matrix -1, 1, 1, and 1. Using skills we've already developed together, it's possible to show that the eigenvalues of the matrix are lambda 1, which is the square root of 2, and lambda 2, which is the negative of the square root of 2. Furthermore, this is an eigenvector associated with the eigenvalue lambda 1, and this is an eigenvector associated with lambda 2. Because the eigenvalues lambda 1 and lambda 2 are real numbers, and because they're not equal to one another, we can be sure that the solution to our problem follows the formula we just encountered. Plugging in the particular details for this problem gets us here. All we need to do now is to find C1 and C2, and for that, we focus on the information given to us in the form of an initial condition. To find C1 and C2, we take our general solution. Then, because we're given a condition on the unknown functions at t is equal to 0, we sub t is equal to 0 into the general solution to get this. Note that the vector here comes from the given initial condition. This statement can be rewritten as a system of 1, 2 linear equations for C1 and C2. Following steps similar to those we've seen many times already, we find that the solution to the equations marked 1 and 2 is this. We can now state the solution to the given initial value problem by subbing the known values of C1 and C2 respectively into the general solution. When we do that, we get, which can be simplified to give us these expressions for the unknown functions u1 and u2 respectively. Plotting the solution to an initial value problem often gives us a better sense of the solution's behavior. We could plot u1 versus t and u2 versus t, respectively, like this. We see that both solutions satisfy the initial conditions placed upon them, and both tend to grow with increasing t. There's another arguably easier way to get a sense of the behavior of our solutions. This other way involves thinking of the differential equations as representing the motion of a particle in two-dimensional space. In this case, the motion would be guided by the vector field corresponding to the matrix A. With this way of thinking, the solution to the initial value problem would represent that path traced out by the particle that begins its journey at the point corresponding to the given initial condition. To construct our sketch in this case, we first lay down the family of eigenvectors of the matrix A on our picture. Recall that the first element of V1 is less than the second, so the V1 family of eigenvectors is captured by this line of slope greater than 1. Recall also that the second element of V2 is negative and smaller in absolute value than the first. This means that the V2 family of eigenvectors is captured by this line of slope that is greater than -1 but still negative. If we were to place a particle exactly on one of the two lines we've drawn, but not at the origin, it would begin to move and would remain on the line on which it started. This movement along the lines over time t is captured by multiplying the appropriate eigenvector by e raised to the power t times the appropriate eigenvalue. Here, the eigenvector gives the direction in which the particle travels, and the exponential term gives us a sense of how far the particle is from the origin. Since the eigenvalue associated with V1 is a positive number, we know that as t grows, our particle will move away from the origin. We represent that movement from the origin with arrows. Since the eigenvalue associated with V2 is a negative number, we know that as t grows, our particle will move closer to the origin. We represent that movement toward the origin again with arrows, but now the arrows point in like this. As a side note, I'll mention that if I did manage to place a particle directly on the origin, it would not move at all, since the origin is in equilibrium or steady state. I've gone to the trouble of laying down these special trajectories because they act like signposts for the solution we actually want to plot. In the problem we studied, we were given an initial condition of -1 and 1. So, in this picture, we put our particle here. Following the signposts, we can roughly predict that the solution will ultimately take us away from the origin in a swooping path like this. Pictures like this are useful because they can show at a glance whether the origin is a stable equilibrium or not, and lay bare for us the nature of the stability or instability. Incidentally, in this case, we would consider the origin to be an unstable equilibrium. It's true that particles, properly placed, would travel toward the origin over time. However, it's also true that we can push a particle away from the origin in a way that the signposts would direct it to tend away from this steady state as t grew. Before we wrap up this lesson, let's recap. We encountered a formula for solving u prime is equal to a times u that assumed a had two distinct real eigenvalues. The formula depended on two constants that can be found using a condition like u at 0 is equal to u sub 0. We applied the formula to study an example. We plotted the results and saw that the solution traced out a curve in u1, u2 space that followed the vector field connected to A. You'll know that you've come to terms with the ideas presented in this video when you're able to do three things. First, you'll be able to solve a pair of linear homogeneous differential equations when the matrix involved in the equations themselves has two distinct real eigenvalues. Second, you'll be able to use extra information like that provided by an initial condition to find a solution to an initial value problem. Finally, you'll be able to devise a sketch of your solution in u1, u2 space using the eigenvectors of the matrix as a guide. Please remember that you can't just watch this video and expect to be able to always solve systems of linear differential equations perfectly. Read the notes to get a better sense of where the formula we presented came from. Explain the formula to a friend or to a classmate. Try the practice problems and make up your own problems and use them to challenge someone else. Basically, I'm saying mix it up. Make learning about linear homogeneous differential equations anything but a homogeneous process.